So, what I've said so far doesn't guarantee anything about the existence of a limit where Newton's constant is actually infinity. But nevertheless, that limit may exist. If that limit exists, the limiting theory is a theory in 11 dimensions. It'll be a supersymmetric, relativistic theory in 11 dimensions, with 11-dimensional supergravity as its low energy limit, and depending on no dimensionless parameters. Does it exist? I haven't the faintest idea. All I'm saying is that, while in the past I would have bet against it, I shall place no such bet today.
Welcome back to ScienceClic. Today, M-theory. At present, we can describe our universe with two main theories. General relativity, which models gravity on a large scale through a curved spacetime, and the standard model of particles, which unifies all other interactions using quantum fields, whose vibrations can be interpreted as particles. In essence, these two models are quite similar. Both make use of the concept of fields, the field of curvature of spacetime for general relativity, and the quantum fields of particles for the standard model. But while relativity is a classical theory, it predicts a precise evolution over time. The standard model is quantum. Its description consists of superpositions and probabilities. Hence, these two theories describe two completely different worlds. At a large scale, general relativity is an excellent description of our universe. However, when we zoom into matter, we have to consider the phenomena of quantum physics. For now, this is not a problem. We can describe the disturbances of the curvature of spacetime as a quantum field, whose fluctuations we interpret as particles, gravitons. We thus determine the quantum behavior of gravity. However, zooming in further to ridiculously small scales, down to a quintillionth of a micrometer, smaller than the Planck length, the calculations no longer work. At this fundamental scale, gravity seems incompatible with the quantum world. How then to reconcile them? How to understand what happens where gravity acts at a fundamental scale, such as at the center of black holes, or during the first moments of the Big Bang? In this video, we are going to immerse ourselves in the abstract world of theoretical physics, in search of a promising framework to solve this problem. Beware, this subject is particularly abstract, and it is recommended to have first watched our string theory video. We are in the 1970s, and researchers are interested in a promising theory: supergravity. Our space-time has four symmetries. The laws of physics remain the same after translations, rotations, the passing of time, and changes of frame of reference. These four symmetries are mathematically included within general relativity. But there might exist another, still hypothetical symmetry called supersymmetry. If we also consider this symmetry, we get supergravity. In essence, supergravity is very similar to relativity. Space-time can bend, generate interesting structures, and even produce singularities without dimension, forming black holes. Physicists also explore supergravity in hypothetical universes with additional dimensions, and the theory then leads to generalizations of black holes with 1, 2, or more dimensions, which form extended objects, membranes, or branes for short. These can have a mass, a charge, and even be supersymmetric. This model is interesting, but once we zoom in beyond the Planck scale, the theory still breaks down. As with relativity, supergravity fails at the fundamental scale. A few years later, in the 1980s, physicists discovered a revolutionary new model, which assumes that all particles are made up of a small strand of vibrating energy, a string. As it also exploits the concept of supersymmetry, we call it superstring theory. when they meet, strings can interact with each other, merge, or divide, and like a guitar string, they have different modes of vibration, which behave at our scale like different particles. With amazement, we discover that one of these modes of vibration behaves exactly like the graviton. For the first time, a theory allows us to describe quantum gravity in a fundamental way. The model is promising, but it sets several restrictions on the universe. The theory imposes that space-time has not 4, but 10 dimensions, with 6 additional spatial dimensions that we have not yet detected. The theory also sets the type of strings that can be studied. If we decide to study open strings, for example, little strands, these can curl up on themselves, and we must therefore also study closed strings, little loops. Taking these restrictions into account, researchers found that superstring theory only allows for 5 possible universes. Type 1, which contains both open and closed strings, types 2a and 2b, which contain closed strings, and 2 heterotic types, SO32 and E8 cross E8, which contain closed strings with different types of vibrations that move in opposite directions. These 5 models are the only possible variations allowed if we hope to describe our universe with superstrings. So which of these 5 versions do we live in? Which truly describes our universe? Let's leave this question aside for now and return to supergravity. At this point, one might think that superstring theory and supergravity are 2 entirely independent models. However, there is in fact an intimate connection between the 2. On a large scale, both describe a supersymmetric universe with gravity. In fact, supergravity, when applied to a universe with 10 dimensions, turns out to be an approximation of superstring theory. This implies in particular that the branes of supergravity also exist in the world of superstrings. Strings are precisely one of the many possible branes with 1 dimension, but there are also D-branes, which open strings can end on, or even NS5 branes with 5 dimensions. The model of supergravity therefore remains useful, and researchers become interested in another unexpected property. Supergravity only accepts a maximum of 11 dimensions, 1 more than in superstring theory. In this 11-dimensional supergravity model, all the constants of the universe would be fixed by mathematics. Unlike with the 5 possible choices of superstring theories, supergravity proposes a new standalone theory to describe the world, at least as an approximation, with 11 dimensions. By the early 1990s, we have a panel of 6 interesting mathematical models. The 5 versions of superstring theory with 10 dimensions and the 11-dimensional supergravity. On top of this, several researchers, and in particular Edward Witten, gradually discover a network of subtle connections, dualities, which relate all these theories to each other. Physicists begin by looking at 11-dimensional supergravity. Amongst many other things, this model contains branes with 2 dimensions. Imagine now that we transform one of the 11 dimensions into a circle and reduce it until it is no longer visible. After this compactification, only 10 dimensions are left, and the branes have lost 1 dimension, becoming strings. In a surprising way, the resulting model behaves like superstring theory, or more precisely, like its 2a version. Before discovering this duality, researchers could only study strings which interact weakly with each other. Indeed, the method used to calculate their behavior, known as the perturbative approach, consists in taking a first estimate and adding small corrections to integrate interactions more and more precisely. If the strings interact strongly, however, these corrections become too large. They cannot refine the result, and even an infinite number of them would not allow us to describe certain phenomena. Discovering the link between these two theories, however, will allow scientists to probe the behavior of strongly interacting strings. To do this, we just need to regrow the 11th dimension that we had compactified into a circle. By adding this dimension, we describe the universe of the 2A theory, but this time for strongly interacting strings. To model this regime, we need an 11th dimension. Similarly, we can compactify the 11th dimension into a line segment rather than a circle. This time, we obtain a description of the E8 cross E8 theory. And again, the link between the two models allows physicists to probe the behavior of strongly interacting strings for which the calculations weren't possible before. Little by little, researchers discover other dualities. For instance, taking the 2A and 2B theories and compactifying each of them on a circle, one large, the other small, we obtain two models that describe the same universe in two different ways. Each quantity in one is related to another quantity in the other. For instance, the speed of a string moving in the compact dimension is related to the number of times it wraps around that dimension in the other description. This is called T-duality. It also connects the two heterotic theories together. As a final example, we also discover S-duality, when strings interact strongly on one side and weakly on the other. We already saw two examples of this with 11-dimensional supergravity, which allows us to model strongly interacting strings within two of the superstring theories. This duality, in fact, also applies to the types 1 and SO32, or more interestingly, to the 2B theory with itself. When we invert the strength of the interactions, the types of branes contained within the theory convert back into each other, such that we recover the original model. In just a few years, researchers discover many dualities which connect all of these theories to each other. Thanks to these dualities, we can transform tedious calculations in one model into simpler calculations in another. These discoveries have allowed us to study phenomena previously inaccessible, and to discover, for example, that the entropy of black holes, the amount of information that they contain, can be calculated by counting the strings which are attached to them. The results are in perfect agreement with Hawking's radiation formulas. This gush of research also led to the discovery of the ADS-CFT correspondence, according to which certain universes can be described as holograms of their surface. In 1995, Witten proposed that there could be a single, fundamental theory of which the 5 versions of superstrings and 11-dimensional supergravity would only be approximations. A bit like half-drawn maps of an unknown landscape, these 6 theories could be partial descriptions, and the dualities which connect them could indicate that they overlap in places to describe the same zones. Witten called this model M-theory, a mysterious name for an equally mysterious theory. Perhaps standing for membrane or matrix, he leaves the freedom to future researchers who will understand it better to decide its meaning. At large scales, considering weak interactions, M-theory would describe an 11-dimensional supersymmetric world containing branes. But at the fundamental level, although everything seems to indicate that it exists, its formalism remains a mystery. It could turn out to be a completely new description of the universe. There are already attempts, such as the BFSS matrix model, according to which spacetime and strings would emerge from a purely abstract description, but research in this area is proving very complex. At present, as with all other theories that attempt to unify gravity and the quantum world, M-theory is not supported by any experimental evidence. Like other theories, it allows for a wide variety of initial configurations with different contents and geometries of spacetime, and we don't yet know which one corresponds to our universe. Just as we cannot probe the geometry of our spacetime at a very large scale, we cannot probe it on a fundamental scale either, at least for now. It stands, however, as the most advanced candidate in the search for a theory of everything, unifying gravity and the Standard Model. For many researchers, it is an elegant and promising theory, which predicts gravity without having to add it to the model. Research around M-theory has opened many doors in both physics and mathematics. In parallel, many other theories have been developed, such as loop quantum gravity, causal dynamical triangulation, or asymptotic safety, which also attempt to unify gravity and the quantum world. Which of these models will allow us to understand the foundations of our universe? Who knows? They may in fact complement each other, leading to an integrated framework of an even more general theory.